so 2-4 is the last section of chapter 2, which means that we are preparing to review and approaching a chapter 2 test. So 2-4 is rates of change and tangent lines. This is probably the most critical connection between where we're going and what we have done. So our goal today is to find the slope of a secant and tangent line. For the remainder of this year, you are going to be asked the question, find the equation of the tangent line, which is going to directly relate back to the concepts and understandings that we are learning today. So, what is a rate of change? Think back to just the word rate in general. In Algebra 2, you learned a rate of change as slope. In physics, you learn rates of change as velocity. In calculus, a rate of change represents both of those ideas. A rate of change is a change in the amount of a quantity over a period of time. It is the amount of change of a quantity over a period of time. It is the change in the interval over the length of the interval. It is delta y over delta x. It is y2 minus y1 over x2 minus x1. Average rates of change are just that, the average change in a quantity over a period of time. Okay? So when it says to find the average rate of change of f of x equals x cubed minus x over the interval 1 to 3, what we need to do is find f of 3 and f of 1. So you have f of 3, which is equal to 27 minus 3. F of 1, which is equal to 0. So the average rate of change is equal to f of 3 minus f of 1 all over 3 minus 1, or 24 minus 0 over 2, or 12. Okay? So again, the idea is that we are looking for averages. Then, as we get further and further into a concept, we want to know, okay, what is happening through various points on the curve? Well, what's happening is what we call a secant line. We describe average rates of change by looking at slopes of secant lines. And we look at what they approach to find the slope of a tangent line. A secant line to a curve is a curve that passes through 2 points on the curve. We find the slope of the secant by using slope of the secant equals f of x2 minus f of x1 all over x2 minus x1. So you will hear me say slope of the secant. Oftentimes I will be like, okay, that's the slope of the secant. Slope of the secant is the average rate of change. A tangent is a line that touches the curve at 1 point. A secant line touches the curve at 2 points. A tangent line touches the curve at 1 point. So a tangent line is the limit as x is approaching x1. So a tangent line is the limit as x is approaching x1. So I look at the limit of the slope of the secant line to find the slope of the tangent line. How do we find that? In the graph below, we are trying to find the slope of the tangent line to the function at the point A, f of A. In order to do this, we choose another point so we can calculate the slope of the secant line. So, here's the big idea. Here's our graph. We are trying to find the slope of that red line. So we are trying to find the slope of this line. That's our goal, to find the slope of that line right there. In order to find the slope of that line, we are going to use the slope of another line called the secant, which is this blue line. So we're trying to find the slope of the red by using the slope of the blue. And our goal is to get h, which is the change or the distance between this point here and that point there, to get as close to 0 as humanly possible. So the goal is to find the slope of the blue using 2 points on the line, to predict the slope of the red by making the distance between the 2 points A and A plus H as close as possible, which is what you were doing when you found the slope or the average rate of change when you looked at the difference from 1 second to 1.01 seconds to 1.0001 seconds, etc. So this creates the following equations. So once we've done that, we create this idea here that we have the slope of the secant is now represented by f of A plus H minus f of A, where A plus H minus A simplifies to H. which means that now the equation of the tangent line becomes the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so again, I think it'll make a little more sense once we look at an example problem. So an experimental biologist is looking at the rates of change of the population of fruit flies grown in a lab. So they're looking at what happens to the population of these fruit flies in a 50-day experiment. So the blue curve represents the equation of the growth of the fruit flies. The first set of equations we're going to do is to represent the change in growth from day 45 to day 23. So we're going to compare the growth from day 45 to day 23. So the average rate of change, or that comparison of growth, would be 150 minus 340 over 23 minus 45, which is negative 190 over negative 22, which is a positive 8.6. So what does that 8.6 represent? Well, what it represents is that on day 23, there were 150 flies. On day 45, there were 345. So what that means is that there was an increase on average of 8.6 fruit flies per day. There was an average increase of 8.6 fruit flies per day. Part B, how fast is the population growing on day 23? So we just compared day 45 to day 23. So what we want to do is get closer in our comparison. So maybe we compare day 40 to day 23. So that's like 330 minus 150 and 40 minus 23, which is approximately 10.6 fruit flies per day. So is day 40 to day 23 going to be the best comparison? No. So maybe we compare day 30 to day 23. So on day 30, that looks to be about 265. So now that's approximately 16.4 fruit flies per day. Is my number of fruit flies per day increasing or decreasing? Increasing. Wouldn't you say that if you looked at this equation over here, that this line appears to have a steeper slope there than the slope here, than even the slope there? So it should make sense that my lines or rates are increasing because the slope here is steeper than the slope there. So let's try to get even closer. Let's look at day 25. Oops, is 175 not good? Sorry, make that 195. So that gives 22.5 fruit flies per day. That's probably pretty close to accurate. Again, we don't know the equation of the blue line, so we can never find the exact. If you wanted, you could also compare day 20, which would be down here, which is at 100. And that would give you the 2 points around it. So again, if you did negative 50 over negative 3, you get about 16.66 fruit flies per day. So again, your average is going to be between that 16.6 and 22.5. And okay, here's the key concept. Find the equation of the tangent line to the parabola at the point 1, 1. So we know that a parabolic curve is increasing on the right and decreasing on the left. So if I'm finding the equation of the tangent line to a parabola at a point 1, 1, I'm looking for basically this red line right here. We are trying to find the equation of that red line. So in order to find the equation of a line, I need two things. I need a point and I need a slope. To find the equation of a line, you need two things. You need a point and a slope. So I'm given the point. I am looking for the slope of the tangent. We previously said that the slope of the tangent is equal to the limit as h approaches 0 to the slope of the secant. So here's my point 1, 1. The slope of the secant comes from some point 1 plus h away from the point I have, where h is this distance, to a new point, which has a height of f of 1 plus h away. So the slope of the secant is equal to f of 1 plus h minus f of 1 all over 1 plus h minus 1. Because again, this is your like f of x2 minus f of x1 all over x2 minus x1, where my x1 is 1 and my f of x2 is 1 plus h. So f is like x squared. So again, y is another way of saying f of x. So this becomes 1 plus h squared minus 1 squared all over 1 plus h minus 1, which becomes h. FOIL 1 plus h squared. And you get 1 plus 2h plus h squared minus 1. Your 1's cancel. And you are left with 2h plus h squared over h. So this is a case where you can cancel the h's on top with the h on bottom, because the denominator is a singular variable. So we get that the slope of the secant is equal to 2 plus h, which means that the slope of the tangent is equal to the limit as h approaches 0 of 2 plus h, which is like 2 plus 0, which is 2. So now I have a slope and a point. So the equation of the tangent line becomes y minus y1, or in this case, 1, equal to our slope, which is 2, times x minus x1, which is 1. Or the equation of my tangent line is y minus 1 equals 2 times quantity x minus 1, which reduces to 2x minus 2 plus 1, or 2x minus 1. Which again, if you look at this red line here, you should be able to see, okay, that looks like it would have a y-intercept of -1 and a slope of up to over 1. Example 3. We found the slope of the tangent line in the previous example at a particular point 1, 1. We can find the slope of a tangent line to any point on a graph by not using a specific point. So the slope of the tangent line at any point would be like using the point A, f of A, and A plus H, f of A plus H. So if we use these two particular points, that will give me the exact slope of the tangent line at any point on my graph. So we can say that the slope of the tangent is equal to the limit as h approaches 0 of f of a plus h minus f of a all over a plus h minus a. And then in this case, my f of x is x squared. So to find the slope of the tangent, we're going to find the limit as h approaches 0 of a plus h squared minus a squared all over a plus h minus a. At this point, you're just doing algebra. This is the calc. Now's the algebra. A plus h squared is really FOILed, so it's a squared plus 2ah plus h squared minus a squared all over h, because a minus a becomes 0 based on the additive inverse. Up here, so again the a's cancel here. A squared minus a squared are additive inverses again, so they cancel. And we get that this is equal to the limit as h approaches 0 of 2ah plus h squared all over h. So you can cancel an h here, here, and here. So this is equal to the limit as h approaches 0 of 2a plus h. Well, you plug in your limit finally, and you get 2a plus 0. Or that the slope of the tangent line to this function at any point is equal to 2a. So what that means is if you wanted to create the equation of a tangent line to any point, the equation of the tangent line would be y minus y1 equals 2a x minus x1 where the a value is the same as x1. So again, this is called the general form of the equation of the tangent, or the slope of the tangent. Example 2 was finding the exact slope. So again, you could even go back and check. In the last example, our x1 and y1 were 1. So if you plugged in 1, 1 here, and then a equals 1, you would get the same equation of the tangent line we previously found. Okay, so be careful when doing your homework tonight. For 9 to 12 today, you're only doing part A. However, tomorrow we're going to be doing B through D. So you may want to leave yourself like 4 to 5 lines after you do problem 9, 10, 11, and 12, so that tomorrow you don't have to do it on 2 separate sheets of paper. You can just go back and fill in B, C, and D. So again, for 9 through 12, leave yourself a few extra spaces. So you have about 15 minutes to start on this now.